Hello, we are now in chapter 9, and this chapter is mostly theoretical, and this is a kind of a wrap up of all the previous chapters. What we will talk about today is assessing studies based upon multiple regression. So, we want to answer the question, how can we tell that the model is reliable? So, we actually need to assess two things. Internal and external validity. Internal means that inside our research everything is according to assumption that we posted. So it is mostly related to population that we studied, the population of entities from which sample was drawn, people, companies, school districts, students, that it satisfies these populations and our sample are satisfying certain assumptions. Those assumptions you already saw, but we will again recapitulate them here. And when it comes to external validity, it actually depends upon the setting, institutional, legal, social, and economic environment. What it actually means is whether the result of our research can be implemented to some other population outside our starting population. Whether, for example, our research about school districts in California can be implemented on districts in some other American state, for example. And it depends upon the maybe different institutional, legal, social environment in these other states. So what are the threats to internal validity? There are two components that we need to take care of. First is estimate a causal effect that it should be unbiased and consistent. In other words, that our assessment beta, our estimate beta hat must be unbiased and consistent. Otherwise, the answers will be invalid. The other thing that we need to take care of is variation in our sample. So hypothesis that should be have desired significance levels, and it is related to the variance in our sample. So standard errors must be unbiased and correct. Both assumptions are actually related to testing, where we are actually using the estimate and using the variance, actually standard deviation calculated from the variance, to calculate the real value of t statistics and to test certain hypotheses. If we do not have unbiased and consistent estimate, if we don't have unbiased and correct errors or standard deviations, then our hypothesis will be wrong. So when it comes for OLS method, under these assumptions, we have unbiased, consistent estimators and variances calculated in a way that gives us correct significant levels. So in that way, we will provide internal validity of our results. What are the threats to external validity if we want to implement our results to some other environment? So it means to what extent we can apply our results. And there are two sources of threats: differences in populations, differences in settings. For example, when it comes to difference in population, if we implement our results about the test scores, results of test scores in California districts, maybe population in some other state that we want also implement our model is different because they have maybe more or they don't have immigrants at all. So the percentage of English learners will be different. Maybe the population doesn't have such high income like households and districts in California. This also can influence our external validity, and student-teacher ratio will be probably different because of that. Because in richer districts you can engage more teachers for students. In poorer districts, in poorer states, it is not possible. Also, the other source of threat when it comes to difference in settings, maybe the way the test is organized is different. Maybe the tests in other states are different, and this is why we will not be able to externally validate our results. What are the possible solutions for that? So maybe pilot study. It means that maybe in the other environment, in the other population, we can get some sample and then to test whether our result holds in these other populations, so that we can maybe collect some data about districts in some other state in United States, and then check if our result of our model will hold there also. We can also control for some variables in advance. Maybe if we know already that we have the different percentage of immigrants or English learners to some other states, then we can maybe have that variable in our model in order to control for the variation and differences in different states. Let's go back to internal validity. So what are the threats to internal validity of multiple regression analysis? Internal validity relies upon, as already said, unbiased consistent estimators and correct standard errors for tests. But there are 5 ways that internal validity might not hold. What are these threats that we need to take care of? So, problem is always the same actually, that we have correlation between independent variable and in errors in our model. So we know that this correlation should be 0 in order to hold all the assumptions. So if we have, for example, this model, and if this, for example, variable x2 is related to error, there is something in this error that is related to independent variable, that then we won't have the correlation 0. First threat is omitted variable bias. So if we have some variable that is not included in the model, but it is actually in error, and that variable is correlated with some of our independent variables. What are the solutions? We have to add the missing variable to the model. If it is possible to collect data about that variable, that is also very important. So we can maybe implement instrumental variable regression. It means actually they're using new variable that is correlated with x but uncorrelated with the error. Some other variable outside the model, if we can find it. Then we need to implement randomized controlled experiments. This is also very important to have independently identically distributed data. And the fourth solution are the panel data. So cross-section data that we can follow through time can be also the solution for omitted variable bias. Second threat is misspecification of functional form. For example, a relationship between x and y is nonlinear, but we are estimating with linear model. For example, this model here, if we have this as our error, we have actually linear relationship, but in reality actually our data are not linear. They have some kind of a curve, so a kind of wiggling, and we need to implement some nonlinear form. So this is actually in a kind of way omitted variable, and we need to put this variable x squared in our model in order to obtain quadratic model, parabolic model for developing the model that best suit to our data. You already know in the previous chapter we already talked about all sorts of nonlinear models, not only polynomial model, but there is also a model based on the logarithms and models based on the interactions. Fourth cause fourth threat to internal validity is also measurement error and errors in variable bias. For example, if we have wrong answers in our surveys, so true model should be like this, and we will collect some data. But there is a measurement error in x, so this x is wrong. Why? Because we cannot pick up the true value of x, we have some kind of measurement error. For example, we do not measure exactly the height of the people or the weight of the people or the student-teacher ratio. Then we will not have the true value of x, we will have x tilde. So instead of x, we will have x tilde. So independent error will involve measurement error in our model. It is a very common thing. For example, if you have some surveys on the street asking people, for example, how much they weigh, and they will never tell you the true value how they weigh, because they are maybe wrong, or maybe they are lying. They don't know actually their weight, or they are lying, and this is why you will have measurement error. So our true model will be like this, so we will have x tilde instead of xi in our model. And the assumptions, if we have measurement error, that measurement error is random. So the correlation between independent variable, the measurement error is equal to 0. And also in that way, correlation between measurement error and error in our model is equal to 0. If it is randomly distributed, then we don't have to fear about this. It is okay. The problem is if this measurement error is correlated with error in our model, then we will have a big problem. If someone is making mistake on purpose, if all our respondents, maybe in our survey, are actually lying systematically in the same way, all of them are maybe reporting that their weight is maybe 5 kilograms less than it should be. If we have random error, then it means that someone will say more kilos, someone will say less kilos, but on average it will be 0 or close to 0. But if they are all reporting that they have less weight than they really have, then we will have a correlation between error and measurement error, and that will be a big problem for us. As long as measurement error is small, even if it is correlated, it is not a big problem. So, for example, our true value of beta hat will actually include not only the true value of beta in population, but it will be also multiplied with this term here, which involves variation of data and variation due to measurement error. But if this variance of measurement error is small, really small, then we will not have big problem for modeling. What are the solutions in order to avoid measurement error? So we need to measure better. The second solution is that we can involve instrumental variables, and the third solution is to model measurement error, but this is a rare occasion that it is done very rarely. Measurement error can be also related to our dependent variable y. So true models should be like this, but instead of measuring the true value of y, we are measuring y tilde, so true value of y plus some measurement error in our model. For example, let's say that weight of people is our dependent variable depending upon the height of the people, but we measure the height exactly, but we ask people how much they weigh. So we will have measurement error in our dependent variable. So our model will be actually like this. We will have y tilde, so dependent variable with error, instead of like this, without an error. So what it means actually, that true value of y will actually have measurement error, and it will be here in our error of the model. It means that we will have bigger standard errors when we develop our model. Fourth threat to internal validity is missing data and sample selection. So if we miss some data, it is really important to find the source of this missing data, why they are missing. So if missing data are random, then only effect will be that our sample size will goes down, but it will not influence our model. But if missing data are based upon the value of one of the regressors, then we will have the problem. The sample will not be representative. For example, if we are collecting the data about the student-teacher ratio in districts across California, but we do not collect data, we are missing the data for all the districts that have student-teacher ratio smaller than 20, then our model will be biased, and we cannot have a representative model because it will only represent the districts that have more than 20 student-teacher ratio. Third case, that missing data related to the value of y. Then if we have some missing data about our dependent variable, effectively that we have biased and consistent estimates. So for example, voting and phone calls, it is a very famous example in history of political elections in United States, where they called people, asking them before the elections for whom they will vote. And at that time, after the Second World War, the phone was owned only by rich people living in urban areas, and mostly those people were voting, they declared that they will vote for the Republican candidate. So they have missed actually to survey the answers about from the population that didn't have phones, and their estimate was wrong because at the end, Democratic candidate won the elections because survey was not representative. Survey was um, limited only to the people who were voting for who voted for the Republican candidate. So that value dependent variable was limited because they didn't have answers for the larger part of the population. Uh, Fifth cause of internal validity is simultaneous causality. For example, usually we are starting from the assumption that x is influencing y, that x is independent variable and y is dependent variable. But sometimes it can be the opposite, vice versa also, that y is influencing x. And then we have actually two equations. For example, advertising and profit. If you have bigger profit, X for example, you can have higher advertisement, more money into advertisement. But the more money you invest in advertisement, your profit will be higher. So you have simultaneous causality between these two variables. The problem is that then you will have a correlation between X and U in the following sense. So if Y has in itself ui and your x is dependent upon yi, so in our equation instead of x we can put this here, you actually have the correlation between x and ui because yi already includes ui in itself. So you have actually a term of error two times in your equation, once separately and once inside x, and this is why you don't have correlation 0 between independent variable and u, and that is the problem. What is the solution? Instrumental variable. So variable that is correlated with x and not correlated with ui. What are the sources of inconsistency, bias, and standard errors? So when it comes to variance of our data, so first problem is heteroscedasticity. When we use estimates that assume homoscedasticity, but errors are heteroscedastic, so we have a bias. To avoid heteroscedasticity, so this is why we are using heteroscedastic robust errors in our model in order to protect ourselves from unequal variance across our data set. The second source is serial correlation, autocorrelation. It is most often in the case of time series data, so when errors are independent, which means there is a large bias in standard errors if we use OLS. For example, if you have one observation and the error in that observation is in some way related to the next observation in your data set, and then that next observation is again correlated to the third observation, and so on. So, for example, GDP data have autocorrelated standard errors, and this is the example. So, if you have, for example, original data, these blue dots, this is our model, and if you have some information about GDP in one period of time, and it is below the average, so you can expect actually that the next information about GDP will also be below the average, and afterwards the third one will be also below the average. So this is actually the showcase for autocorrelation between your errors, because sequentially you see that we have correlated errors in this example. This is the problem that will be solved, but time series data are not our subject at the moment. So what are the consequences if we have correlated standard errors? Because it can be also in a cross-sectional data. Standard errors will be too small and t-values will be too large. Because of that, estimates, betas are good, but standard errors are the problem. In order to detect that, we can use Durbin-Watson test to diagnose autocorrelation. And the last slide, sometimes we do not have to satisfy all the assumptions. It depends on the goal of our research, of our example. If we just want to do forecasting, we do not need causality or unbiased estimates for forecasting. We can do forecast even if we have causality and unbiased estimates. So if you want to predict what will be the test score for certain value of certain student-teacher ratio, we can do that although we have causality or unbiased estimates. But if we want to explain the relationship between student-teacher ratio and test scores, then we need to satisfy all the assumptions that we have. The problem with forecast is actually the problem external validity, and it means whether it will be worth for outside our data set. This is the only problem that we have with the forecast. Okay, this is the end of presentation.